Okay, so today we're going to talk about how to find instantaneous velocity and acceleration from a position versus time graph, and then how to use the power rule to find velocity and acceleration. Some of the stuff you might already know. So go ahead and look at number 1 yourself. Think about how you would do it, and then pause the video and then come back in. Okay, so now that you've thought about number 1, let's go through it together. So for A, we want to find instantaneous velocity of the object at 2 seconds. So this is a position versus time graph. So to find velocity, we know that is the slope of a position versus time graph. So to find instantaneous, this is when we have to draw a tangent line. And it should be a straight line approximately. Sorry about those things popping up, at 2 seconds. And then at 5 seconds, we'd have to do the same thing, draw a tangent line at 5 seconds and find the slope there. And again, you'd have to use rise over run technique. So let's see, at this one right here, let's see, we go up. Okay, so it looks like we go up about 6 meters, and then we go over, I'm going to approximate that as about 1.5 seconds. So the slope again is rise over run. So that is 6 meters over 1.5 seconds. And I use the units to help me too. So that looks like that's 4 meters per second. And I know meters per second is units that is appropriate for velocity. Okay, let's look at this other one. So this one's going to be a little bit trickier. I'm going to say that base looks like we're about going over 1 second according to our scale. This is all a little bit of approximation. So we go up. And I'm going to say we go up about 12 meters. So slope right there is rise over run, which is 12 meters per 1 second. So that's 12 meters per second. Cool. Okay, so in general, let's go ahead and look at these 2 questions I have below. So if we're looking at a curve on a position versus time graph, instantaneous velocity. So we know we would need to find the slope of the graph, which again, we'd have to draw a tangent line to do that. So tangent line at that point. In calculus, the slope of the graph is called the derivative. So we would find the derivative at that point. And again, the derivative is the slope of the tangent line at that point. So how we write that in calculus is we write v equals dx dt. And this means it's the derivative of position with respect to time. So that's how you would say that. And I want you to think about, if we think of our equation for average velocity we know is change in position over change in time. That looks pretty similar to dx dt, while d dt means that it's like a very infinitesimal, like very small interval that we are looking at. Cool. Kind of cool that those are similar. Okay, so same thing, let's go ahead and go down and let's look at the next thing. I want you to try number 3 to yourself, thinking about how you would find instantaneous acceleration. Think about what the wording would be. Okay, so now that you've tried it yourself, you know if we have a velocity versus time graph, instantaneous acceleration is going to be the slope of the graph, again, tangent line at that point. Tangent line at that point. That was silly that I rewrote it. I should have just said it's exactly the same. Okay, and to write that, acceleration we know would be dv dt. So again, that would be the derivative of velocity with respect to time. And again, we know average acceleration is change of velocity over change of time, so that looks pretty darn similar. Gosh, that's fun. Okay, so now we're going to go ahead and introduce the power rule. So this is going to be pretty darn cool. So just in general, I want you to think about, let's say this first graph is, let's say, an x squared graph. So, or you know what I should say? I should say it's like a t squared graph would make, x squared is fine. Cool. So let's say this is about x squared graph. So think about if that is like a position versus time graph. Okay, so if you go from position versus time to velocity versus time graph, this would be speeding up in a positive direction. Again, that would mean it should be t squared. Silly me. So the velocity versus time graph would look something like this. So then if you were to go from a velocity versus time graph to an acceleration versus time graph, again, you have to take the slope or derivative. So it's moving at a constant rate. The slope is constant, moving in a positive direction. So it's just going to be a straight line like that. And again, if you were to go, let's say this is acceleration versus time graph. Again, if you take the slope or derivative at that point, the slope is 0. So it would just be a graph like this. So again, this is just the derivative going from here to here We're just taking the derivative for the slope. Okay, so here is the power rule. So if y equals x to whatever n power is, then the derivative dy dx is going to be n. So we're going to essentially take down that exponent times x to the n minus 1. So let's go ahead and try that out with a couple. So if y equals x squared, then dy dx equals, so we bring down the 2, times x to the 2 minus 1, which is just going to be 2x to the 1. And I want you to look up at the graphs above. Those actually graphs would work perfectly for this. First graph is x squared. The derivative of x squared is just going to be 2x. So this next graph looks like that is essentially a 2x graph. Okay, so we know if we take the derivative once more, it should just be a constant. Let's go ahead and prove it with the power rule. So dy dx, so this is like 2x to the 1. So we do 2, the 2, any number out front just stays there, and you just multiply it down. So the 1 comes down, so it's 2 times 1 times x to the 1 minus 1. So this is 2x, 1 minus 1 is 0. X to the 0 we know is just 1, so this is just 2 times 1 equals 2. Cool. So this is y equals 2. Okay, so if you had a function where it was y equals 2, the slope of that is nothing. The derivative would be 0. Let's go ahead and prove that with the power rule. If you have just y equals 2, you can think about it conceptually again. The slope of just a flat line is 0, but we could add some numbers in there. So let's call this an imaginary x is 0, kind of like what we had right here. So we're going to pull down a 0. So this is just 2 times 0 times x to the 0 minus 1. So this is 0 times x to the minus 1. 0 times anything is just 0, so that's just 0. Cool. So then this would just be y equals 0. Okay. So we just used the power rule to take the derivative 3 different times of like a function. And again, if we went through, we'd say like this graph right here is the first derivative, this is the second derivative, and this is the third derivative of the function y equals x squared. So now let's go ahead and look at number 4. So find the derivative of the function y equals x squared at x equals 2 and x equals 5. Take a guess how you do that and then watch back into the video. Okay, so to do that, first we have to take the derivative of y equals x squared, which again, we already did that, but we can do it again. So bring that down, so dy dx is just going to be 2 times x to the 2 minus 1, which is just 2x to the 1, or we could just say 2x. So now we can just plug in. So at x equals 2, plug those values. So at x equals 2, let's see, dy dx is just going to be 2 times 2, which is just 4. And then let's go ahead and do it at x equals 5. Dy dx is just going to be 2 times 5, which equals 10. Cool. So I want you to go back to our beginning intro. So I'm going to go ahead and scroll up. Initially, oh my goodness, this is so cool. Physics is fun. Okay, this graph right here is essentially just like a t-squared graph. So cool. At 2 seconds, we just found that the derivative is going to be, what was it? It's going to be 4, which is exactly what we found from doing approximation methods. At the other interval, we found it to be 10, which is not too far off from our approximation of 12. So cool. That's just how conceptually like it works out. Okay. So now we just have a bunch of practice problems of finding the derivative. What I would do is, if you feel totally great on this stuff, I would pause the video, try number 1 through 8 yourself, and then check back in. I'll explain how to do each one too. So again, power rule, let's practice it out. So for the first one, dy dx, essentially you take the 8 down, so equals 8 times x, 8 minus 1. You take away 1 from the exponent, so that's just 8x to the 7. Cool. Let's go ahead and do the next one. So we take the negative 2 down, and then we take away 1 from the exponent. So that's negative 2 times x to negative 2 minus 1. So that's just negative 2x to minus 3. Cool. Next one, same idea. The 2 is already out front, so that just stays there. We bring down the 6, so that's 2 times 6 times x to the 6 minus 1. So that's just 12x to the 5. Cool. Same idea with fractions. So this is just dy dx, 3 stays there, times 4/3, x to the 4/3 minus 1, which is just 4x to the 1/3. Cool. Let's keep on going. So this one, dy dx, is going to be negative 1/5 times negative 5, x to the -5 take away 1, which is -6. So that is just going to be x to the -6. Cool. Next one, number 6. All right, did not leave enough space. dy dx. This is just 9x to the 1. And so that is just going to be 9 times 1 times x to the 1 minus 1, which is just 9x to the 0, which is just 9. And I want you to think about conceptually, for number 6, that would just be if you had like a graph. Let me draw a little space right here. If you had a graph, y versus x, this would be a graph of y equals 9x. So then I want you to think about the slope. The derivative is the slope. The slope of that graph is always just 9, whatever those units are. Cool. Same thing for number 7 conceptually. If you have a graph, that would just look like if you have a y versus x. That's just going to look something like that. The slope of this graph, there is no slope of this graph. It is 0. So the derivative is going to be 0. But we can prove it too doing the imaginary, like x is 0 next to it, which x is 0 is just 1. So that still is going to be dy dx equals 0 times 100's already there, x to the 0 minus 1. Doesn't matter anything else though, because that is just going to get us 0. Okay, number 8's tricky. If you want a trick, I would think about how you can rewrite 1 over x and then try taking the derivative. Okay, so after you've tried that yourself, we'll try it together. So oh my goodness, sorry. First I'm going to rewrite it. I'm going to say this is like 7 times x to the minus 1. So then if I take the derivative, dy dx, this is 7 times the -1 comes down, and then it's going to be x to the minus 1, take away 1. So this is just -7x to the -2. And you got all sorts of fun derivatives. Awesome. We're now going to go ahead and use this using a couple physics functions. Okay, so now let's say a particle moves in a straight line with its position x given by the equation x of t equals this. What I would go ahead and do, try this whole problem by yourself. And so go ahead and pause the video, try these problems, and then check back into the video. Okay, so now that you've tried it yourself, let's go ahead and go through it together. So find its position after 1 second. So they gave us a position function. We can just plug 1 second in. So x of 1 is just going to be 3 times 1 to the 4th minus 4 times 1 squared plus 5 times 1, take away 8. This is just going to be what? 3 take away 4 plus 5 take away 8, which I'm just getting this to be -4 meters. Okay. So now for B, it says find an expression for the velocity as a function of time. Okay, so they gave us the position function. We want to find velocity as a function of time. This position is changing all sorts of ways. We're going to need to use the derivative, which again, to take the derivative, we're going to need to use the power rule. So I'm going to say B is going to be dx dt. So let's take the derivative of this function. So that's going to be 4 times 3 t to the 4 minus 1, take away 4, again bring down that 2, times 2 to the t 2 minus 1, plus this is like 5 times that 1 comes down, times this is t to the 1 minus 1, and then again 8, this is like 8t to the 0, so that is just going to be take away 8 times the 0 comes down, and this is t to the 0 minus 1. Cool. Which again, that last term, we know that last term, 8 times 0 is just going to be 0. So that last term is 0. And again, if you have just like a graph of just 8, wherever that is, we know that the slope of a graph of just 8, there is no slope, it's 0. So we know the derivative has to be 0. So that's another way to think about it too. Well, let's just simplify this function. So now this is just 12t cubed minus, sorry, that was floppy. Okay, minus, what is this? 8t to the 1 plus what? This is just 5t to the 0, and t to the 0 is just 1. Cool. So that is our function, is our velocity function. Cool. So now for C, it asks for it at 2 seconds. We can just plug that into the function we just got. So v of 2 is just 12 times 2 cubed minus 8 times 2 plus 5. When I plug this into my calculator, I get 85 meters per second. Cool. Let's go ahead and look at the next one. So the next thing asks for its acceleration after 3 seconds. Okay, so we found the velocity function. We know acceleration is just the derivative of velocity, or you could say it's the second derivative of position. So you take the derivative of position twice. So let's go ahead and take the derivative of this function we already found. So let's see, let's go ahead and go through that. So again, we bring the 3 down essentially. So it's 3 times 12 times t to the 3 minus 1. Take away, we essentially bring down that 1 times 8 times t to the 1 minus 1. Again, the derivative of just a number is just 0 because the slope is 0. So we'll just simplify that. So this is going to be 36 t squared, take away 8. And that is going to be our acceleration function. So now we need to find it at 3 seconds. We can just plug that in. So a of 3 is just what? 36 times 3 squared, take away 8, which is just 316 meters per second squared. Cool. I just have one last little one, and then we'll call it a wrap. Okay, so we want to find what time is the acceleration equal to 136 meters per second squared. Well, we got our acceleration function, so we can just plug that into the acceleration. So I'm going to just rewrite my function. It just helps me avoid any silly mistakes along the way. So we have 136 equals what? 36t squared minus 8? Cool. Let's go ahead and just solve this for t squared first. So 136 plus 8 is just 144 equals 36t squared. I'm going to divide both sides by 36. And then that's going to be what? 4 equals t squared. And then we can take the square root of both squared. So we know when we take the square root, it's always going to be plus or minus. So it'll be plus or minus 2 equals t. But in this case, negative times don't make sense, so it is just going to be 2 seconds. Awesome. Thanks for watching.